Hello once again, class, and welcome to another mock lecture. Today we're going to be discussing positional numeration with different bases. But we're going to start out by looking at base 10. Okay, so here's the number, what is this? 10,324,025. Each of the spaces, each of the positions of this specific number has a name, right? There's the ones, the tens, the hundreds, the thousands, the 10,000s, the 100,000s, the millions, and the 10 millions. But more specifically, these are all powers of 10, right? That's why we have a base 10 system. So each position has a base of 10 raised to a specific power. So the ones position is the 10 to the zeros place, right? The tens position is the 10 to the first. The hundreds position is 10 squared. Thousands is 10 cubed, right? So on and so forth. And we just progress this way as the number gets bigger. When you count in base 10, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you start over, right? Then you do 1, 0, right? These are all the usable digits, so you can't exceed a number that's bigger than 9 in a digit place, because then you just go 1, 0, 1, 1, 1, 2, 1, 3. Of course, we call them 10, 11, 12, 13, 14. Then you get to 19, and then you go 2, 0, right? So 20. So let's discuss a different base. Let's talk about base 7 for starters here. Base 7 follows the same principles as base 10. So the positional numeration, the ones position is 7 to the 0. The sevens position would be 7 to the first. The 49's position would be 7 squared. And then the whatever, I think it's 320 something's position is 7 cubed. So one thing that I do, when you're counting numbers is I pretend that I only have 7 fingers. I think counting in general is kind of misleading for base 10 stuff because, really we should only have 9 fingers if you're counting base 10. But that's how it is. You count to 10 and then you start over and you're like, okay, I've counted to 10 now. Well, here you're really counting to 7, right? So 0, 1, 2, 3, 4, 5, 6. 7 is not a digit in base 7, just like 10 is not a digit in base 10. 9 is the highest digit that you can have. So when you're counting, when you get to 6, now you go to 1, 0, right? That's how the counting is going to work in a base 7. And to be specific, right, I can't just leave these as like 1, 0, 1, 1, 1, 2, 1, 3, because if you just take this out of context, you don't really know that it's base 7. So you can put a little subscript of 7 behind the number to let the reader know, oh, this is not a normal base, right? This is 1, 0, base 7, which, by the way, is how you'd read this number, right? 10 as a word doesn't mean anything in base 7. So this is 1, 0, base 7. Then you have 1, 1, base 7, 1, 2, base 7, 1, 3, 1, 4, 1, 5, 1, 6, base 7. And then you go to 2, 0, right, base 7. So here's an example of a number in base 7. We have 1, 1, 2, base 7. I just put the 0 there because I wasn't using the 7 to the third position, right? So I'm not going to say 0, 1, 1, 2, base 7. I'll just say 1, 1, 2, base 7. Now this number, we could figure out what the value of it is in a base of 10, right? So what is this the same as? Like how many actual things do we have when you have this number, 1, 1, 2, base 7? Like this person says, oh, well, let's split up 1, 1, 2, base 7 pieces of chips. I don't know why I'm using that as an example, but something. You have something you're splitting up. How many is that? Well, this is the same, and this is the cool thing about positional numeration. This tells you how many 7 squareds you have. This tells you how many 7 to the firsts you have. This tells you how many units, right, that you have in this case. So this is really, you can break this up mathematically into being 1 times 7 squared plus 1 times 7 to the first plus 2 times 7 to the 0, which is 49 plus 7 plus 2. So this is 58. This is the same as 58 things in a base 10 setting, right? And I'm only using base 10 because that's what most people are going to be most comfortable with. But of course, 58 is not a number in base 7. This is just the base 10 value of the number 112 base 7. Here's another example. Let's say that we want to write the base 10 number 625 in base 7 positional numeration, right? So what base 7 number has a value, a base 10 value of 625? Well, first we should start off by seeing how many 7 cubes go into 725. 7 cubed is 343. And so I'm going to divide that into 625. It only goes in once, though. because if you multiply 343 by 2, you get 686, which exceeds 625. So, okay, it only goes in one time, and that's fine. So with the division, you get a remainder of 282. So that's the number that's left over. So 1 7 cubed piece went in there, right? If you're thinking about it in terms of the base pieces that we have, 1 7 cubed piece goes inside of that thing. So you'd have one long flat base piece, base 7 piece, right? That can be used for 625, and then now we're going to move to the flat pieces. So I'm going to divide 282 by 49, right? Because this is the 49's place. 7 squared is 49. So how many flats can be used to represent the number 625? We already know one long flat can be used to help represent 625. Now how many flats can be used? Well, let's divide the value of a flat, which is 49, into 282. It goes in 5 times, right? If I do the subtraction there, I get 37. So 5 goes in the 7 squared position of this number. Okay, as far as the next number goes, we're looking at how many 7 to the firsts go in there. So this is a long, right, according to the base pieces. How many long pieces can we use to represent this number? So let's divide 37 by 7. Also goes in 5 times. So 5, 7 to the firsts. The remainder is 2, and at that point we're just at the units stage. So there's 2 7 to the 0 piece. There's 2 units, right, that can be used to construct this piece. Okay, and then we're done. So 625 as a value can be represented in base 7 with the number 1552 base 7, which is how I would say this: 1552 base 7. Now there's one more thing that I want to talk about as far as how we can visualize how to count in different bases. So still using base 7 here. I think the counting on your fingers thing is not the greatest way to think about how to count in a different base. Instead, I think it's best to think about as some kind of a clock. And so pretend you have a clock with only the digits in base 7. So 0, 1, 2, 3, 4, and 5, and 6. Okay, and then just start rotating the hands of the clock, and that's how you count in base 7. So 0, right, where both hands are on 0. The next one is 0 and then 1. So 1, right, then 2, 3, 4, 5, 6. And then once we get back to here, now we're adding, we've already gone around 1 time, so now we're adding 1 to the 7's place, because now we're at 1, 0 base 7. Right, so then we have 1, 1 base 7, 1, 2 base 7, and then so on and so forth until you get to 2, right? Then we'd make this 2. When this is at a 6, and then you go through a full rotation, then this one becomes 1, right after that. So that's how counting. That's how I visualize counting in a different base. Think about a clock face. Okay, let's talk about base 12. Right, so we've talked about a base that's smaller than 10. What are bases that are bigger than 10 going to look like? Well, for base 12 stuff, there are going to be 12 digits. So we know 0 through 9 are going to be used. You could say that the number 11 is a digit, and then the number 10 is also a digit. But there's this whole society called the Dozenal Society. Is it of America? I don't know. It's the Dozenal Society of something that are actually pushing for base 12 as being the standard as opposed to base 10 stuff, because it makes more sense when you're counting, and I'll kind of go into it a little bit. But for now, I just want to talk about what are the extra digits in a base that's bigger than 10. So what they came up with was the 10 digit is this upside down kind of rotated 2, and the 11 digit is an upside down kind of rotated 3. Kind of looks like epsilon, to be honest. But those are digits that read 10 and 11. I don't really know how you would read a number, that looks like this. I'm just going to do my best to draw this. I don't know what that number is. But this is, this is in the 12 squared position. This is in the 12 to the first position. This is in the 12 to the 0 position. I don't know why I changed the orientation of the numbering there. But this digit is 11, right? This digit is 10, and that digit, of course, is 9. So, and the reason that this is actually kind of cool, and I'm not saying that I'm part of the Dozenal Society, but it is kind of neat to think about, especially when you think about counting via a clock, because it's just a clock, but you've now replaced the 10 and 11 numbers on the face of a clock with now their digit representations, right? So this is 10, 11. This thing is actually 12. 10 base 12 is 12, right? I mean, it has the value 12, but of course we would say that it is the number 10 base 12. So the reason why a lot of there is a decimal society in general is simply because you can divide 10, right? 10. You can divide 10. 10 has more divisors, right? In base 10, 10 has the divisors 2 and 5, and that's it. But in base 12, you actually have got 4 divisors, right? 10 base 12 can be divided by 2 base 12. It can be divided by 3 base 12. It can be divided by 4 base 12. It can be divided by 6 base 12. So it's easier to find things like thirds or fourths or sixths, and halves still work. The only thing you get with base 10 stuff is fifths are a little bit easier to find, but something as easy as fourths isn't, right? 10 divided by 4 in base 10 is 2.5. So now we've got decimals. Well, that's not a problem in base 12. So I do have to say it is a little compelling of an argument to move to base 12. Let's do an example. Let's say, what is the value of 1875 base 12? Okay, well, 1 in the 4th position, right, of a base 12 number. That's 12 cubed. Then we've got 8 12 squareds, 7 12 to the firsts, and 5 units. So 5 12 to the 0. And then it's just a bunch of math from there, right? And you end up getting 2,969 in the base 10 value. Okay, so positional numeration is really just this, knowing that your base, this thing represents your units, this represents your longs, this is your long flats, this is your long flats, then you've got the piece after that, that's 12 to the 4th. In this specific example, so on and so forth. And so that's different bases. Now, our book does talk about base 60, and it can be a little weird. The digits, as it were, go from 0 to 59. So 59 is a digit. It's one digit, which, of course, is weird, but that's how you have to think about it. So a number like this, right, is a number. 1, 23, 57, 24, base 60. That's a number, right? And there's only 4 digits in that particular number. So this is your 60 to the 0. That's your units. This is your 60 to the first. This is your 60 squareds position. This is your 60 cubes position. That's the worst 3 I've ever drawn in my life. But there you go. Okay. So hopefully this was helpful. Different bases is really interesting, but really the same as base 10 stuff. You just have to think about, what are we doing when we're counting, right? Why do we go back to 10? That sort of thing. So thanks a ton for watching. Leave a comment if you have any questions, and I'll see you in the next one.